Welcome to this video on forces and moments. It is one of several videos in a short course on equilibrium posted at terje.civil.ubc.ca, Toolbox, a website that contains notes, examples, and algorithms for structural analysis. Please visit the website for more videos and other material relevant for this course. The next slide is intended to make 2 points. The first is that forces and equilibrium are basic and now intuitive concepts with a long history, even in Western literature. In the context of structural analysis, equilibrium essentially means the balance of forces. On the left-hand side of this slide is a structure drawn by Galileo in 1638. Although Galileo was then establishing the field of solid mechanics, namely the study of how the material inside this column behaves, the figure serves as a simple example of equilibrium of forces. Whichever forces are pulling downwards must be matched by forces pulling upwards. In the same century, in 1687, Newton published his famous 3 laws of physics. The first law addresses global equilibrium of the body in question, in this case a column attached to a rock. The 2 blue arrows must represent equal force values with opposite directions. In other words, there must not be a net force acting upon this assembly. Newton's second law says that the column would move with constant acceleration if there was a net force. The third law applies to every interface at any imaginary cut, anywhere from top to bottom of Galileo's column example. The 2 red arrows illustrate the point. The upwards force in the hook that holds this rock in place must equal the downwards force from the weight of the rock. The next slide emphasizes that last point. The figure shows a beam that is cut at the middle. The point Newton made in his third law is that whatever forces act upon one of the surfaces of the cut must be equal and opposite on the adjacent cut. This is an important law to remember in structural analysis. The next slide highlights the important role that equilibrium plays in structural analysis. Additional equations will be needed in many situations, but equilibrium is always part of the considerations. Consider the simple building structure shown here. It is clear that no amount of material strength would prevent this building from collapsing if the ground is not resisting with a force at the location of this question mark. Equilibrium is also central in the determination of the force in each member of a truss structure. We do that by considering equilibrium at each joint of the truss. In advanced structural analysis, covered in other material on this website, the principle of virtual displacements actually represents equilibrium. That leads to the equilibrium equations of matrix structural analysis and the finite element method, here expressed as the stiffness matrix times the displacement vector. That matrix vector product equals the external forces on the structure, which is an expression of equilibrium. The concept of stress, addressed in another course, is also an expression of equilibrium. In its simplest form, stress is essentially a force spread out over an area. In fact, Augustin Cauchy used this tetrahedron in his equilibrium considerations when he introduced the concept of stress in 1822. Even in the Euler-Bernoulli beam theory, it is necessary to amend the regular derivations, which only include axial stress, with equilibrium in order to recover shear force and shear stress. Several of the applications on this slide are outside the scope of the present course, but they suggest that equilibrium is always important. On an earlier slide we saw that equilibrium is the balance of forces. That concept is now extended to moments, which are introduced in this slide. Abstractly speaking, a moment is an angular force. Practically speaking, a moment at a location is the value of a force acting at some distance, multiplied by the distance to that force. More precisely, that distance is the smallest distance to a straight line that goes through the force arrow. That distance is called the moment arm. Using that definition, moment is force multiplied by arm, where arm means distance from the force to the point where the moment is calculated. Now consider this seesaw. A quick glance tells us that it might be in equilibrium. That is because we intuitively consider moment equilibrium by the support, and observe that the moment of the heavy elephant on the left-hand side, that acts with a small arm, might very well equal the moment from the lighter dog because that force acts with a larger arm. The next slide takes advantage of the seesaw example on the previous slide to identify 3 types of equilibrium. Here we are not considering dynamic equilibrium, which becomes relevant in structural dynamics. On this slide, the first type of equilibrium, which we always seek for our structures, is stable equilibrium. Galileo's column is an example of that. Conversely, the seesaw example is an example of neutral equilibrium. That is because we can easily see how a small perturbation would lead to movement of the seesaw. In fact, if we think of an advanced model that accounts for the elephant stepping forward if the seesaw starts tipping the dog's favor, then this is an example of unstable equilibrium. In other words, a small perturbation would lead to a big change in the picture. The rolling balls at the bottom of this slide show an abstract yet intuitively appealing way in which to visualize stable, neutral, and unstable equilibrium. The next slide shows some of the loads that act on buildings. It is loads like these that create forces in the structure and its supports. This building is subjected to snow load, wind load, dead load, which is gravity load from weight of the materials that the structure is made of, live load, which is gravity load from the contents and users of the structure, and lateral load from ground motion caused by an earthquake. Notice that snow load acts per unit length of the roof's vertical projection. Also, notice that the building code prescribes that the wind load acts per unit length of the inclined roof, in the direction perpendicular to the roof, and that the dead load acts vertically per unit length of inclined members of the structure. The load from earthquake ground motion is in reality more complex than what is shown here. However, a simplified approach in the building code is to consider the effect of an earthquake as static lateral load on the structure. Newton's second law suggests that that load is proportional to the mass of the building. Although many factors play into the calculations, it may not be unreasonable to say that this simplified earthquake load is 25 to 50% of the building's weight. To reinforce the concept of a moment, this slide shows a cantilevered beam subjected to a force, F, at the tip. The length of the beam is denoted by L. That means the moment at the base of the cantilever equals the force times the arm, namely F times L, as the title of the slide says. This is an example of going from force to moment. Next, we go all the way from a uniformly distributed load to a resultant force and then to a moment. This cantilevered beam is subjected to a distributed load denoted by Q. One method for determining the moment at the left-hand side base of the cantilever is to first determine the resultant of that distributed load. By summing or integrating the load along the full length of the beam, we find that the total load is Q times L. In other words, the resultant force is Q times L, here denoted by R. That resultant acts at the middle of the beam because the load is uniformly distributed. The moment at the base of the cantilever is now calculated in the same manner as on the previous slide. Multiplying the force, Q times L, with the distance from the base of the cantilever to the force, namely half of L, gives the moment QL squared over 2. The next slide shows a situation where the distributed load is not uniformly distributed. The full length of the beam is still equal to L, but the load intensity now varies from 0 on the left to Q on the right. Because of that triangular shape of the distributed load, we must introduce the factor 1/2 when we integrate or sum all the load along the beam. Moreover, the distance from the base of the cantilever to that resultant load is now 2/3 of L. The reason is seen in the mini formula sheet shown on the right-hand side of this slide. Here we see that the area of a triangle contains the factor 1/2. We also see that the distance from either end of the triangle to its centroid is either 1/3 or 2/3 of its length, depending on which side we measure from. In the end, the moment at the base of the cantilever is the resultant force times the arm, which multiplies to QL squared over 3. The previous slides introduced the concept of a moment as an angular force, shown as a semicircular force at the base of a cantilever. A moment can also be seen as a force pair. Intuitively, it is possible to see that this beam is in equilibrium. That is because you can see that the force pair on the left-hand side is able to carry the moment that develops from the force F acting with the arm L. This is one simple example of seeing a moment as a force pair. The next slide demonstrates the same concept, but this time for a truss structure. A truss structure means that the members can only take axial force. This particular truss essentially acts like a beam to carry the uniformly distributed load placed at the top. Without getting into a detailed truss analysis, the top chord will develop compression. Conversely, the bottom chord will be in tension in order to carry the load on the truss. That force pair, which consists of a force at the top and a matching force at the bottom, is a moment. In the analysis of beams, such as the simply supported beams shown at the bottom of this slide, we do indeed find this kind of moment acting inside on the cross-section of the beam. More about that in other videos. Thanks for watching this video. Please visit terje.civil.ubc.ca Toolbox for more videos and more material relevant for the modern structural engineer. See you soon.